Okay, so today we will continue our method of Gaussian elimination. Let me start with a recall. So you remember that we start from a system of linear equations that I call S, and we associate to that so-called augmented matrix, which is composed on the left part from the matrix with entries, the coefficients A, I, J, and on the right part of a vertical bar you put the values B1, Bm. Then we have seen that if we start from any such matrix, we can associate to this by elementary row operations of three types. Remember, we can swap two rows, we can change a row and multiply by a non-zero scalar, or we can add to a row a multiple of another row. Those are the three elementary row operations. Now the aim of this transformation is to get RREF, which stands for reduced row elementary form. Such matrix will be easier to read actually the solution of the system. In this session we are going to practice and give two examples of computation, and we will finish by some further application of this Gaussian elimination. So first of all, we are going to see the Gaussian elimination algorithm. So algorithm meaning the process that will associate to any augmented matrix RREF form. Okay, so what is the procedure to do that? First, step one, if the cursor entry is 0, then we swap rows to get a non-zero cursor entry. This is step one. Step two, we will make the cursor entry equal to 1. This is our pivot. Remember that in the RREF form, the first non-zero entry of each row must be a 1, and this is called a pivot. Now, step 3, we make all the other entries in the same column equal to 0. And step 4, we move the cursor down one row and to the right. Okay, that's basically the algorithm we will follow. However, I think the best way to understand this algorithm is just to practice with some concrete exercise. So let's practice this with our first example. Now I'm going to start with a system. So here the system will be the following. 3x plus 2y minus z equal 3. X minus y plus 2z equal 4. 2x plus 3y minus z equal 3. Okay, so starting with this system, the first step is to get the augmented matrix. How do we do that? Okay, this is very easy. You will take, first of all, we will have how many rows and how many columns for this augmented matrix? Well, the number of rows is the number of equations. So we will have 3 rows, and we will have, so the number of columns will be the number of variables and also the column for the b's. Therefore, 1, 2, 3, 4 columns. Now, the coefficients, well, you put the aij. So the first is 3. This comes from this 3x. And then, as you can see, we have 2, minus 1, then my vertical bar, and here 3. The second row, so 1, minus 1 coming from here, this 2, and then 4 coming from here. The last one, 2, 3, minus 1, and 3. Okay. So, now I'm here, okay? I have associated to my system an augmented matrix. The next step will be to apply this algorithm to get a RREF form of this augmented matrix. So, let's do that. First of all, better than to follow mechanically the algorithm is to choose the right move. Okay, there are several possibilities to get from one matrix to our RREF, but there are clever ones. Don't forget that ultimately we want a pivot. Okay, so we want a 1, and we start always the cursor. The starting point is always this here, upper left corner. So here we would like a 1. Now we have different possibilities to get a 1. We can divide by 3 this row, or we can swap. Don't forget that we can swap. Then here, obviously, swapping row 1 and row 2 will be very effective because we will get a 1 here. So that's our solution. So we are going to write a map, and here above we will write the operation that we are using. So here we are going to use a swapping of row 1 with row 2. Okay, so what is the result? Result is that row 1 becomes row 2 and row 2 becomes row 1. So, okay, 1 minus 1, 2, 4. Don't forget to change the right hand side also. Huh? Okay, so my row 1 became row 2, sorry. Now I write the row 2 who became the row 1, so 3, 2, minus 1, and 3. And then the meaning is that I'm just doing this operation on the first 2 rows, but the third row remains unchanged. Therefore, 2, 3, minus 1, and 3. Okay, so this is step 1. Now, the next step is to move the cursor. Here we reach already step 2 because we make the cursor entry equal 1. This is our new pivot. This is our first pivot actually. Now we are here. So the step 3 is to make the other entries here and here equal to 0. Now how do we do that? We use the pivot. How do we use the pivot? Well, we are going to modify, as you can see, row 2 and row 3. We want to replace this and this by 0. We want 0. Okay, how do we do that? First of all, I'm going to modify row 2. Now, row 2 has a 3 here. And here I have a 1, which is called my pivot. I'm going to use my pivot, so I'm going to subtract 3 times row 1. So sorry, in my notations, remember my notation? So I modify row 2, and I'm going to subtract 3 times row 1. So this is written in this way. Now row 3, I modify row 3, and row 3, I'm going to subtract 2 times row 1. So 2 from here. Okay. So if I do these 2 operations, I should get the following matrix. You will check. So please check that I'm not doing any mistake. So the first row is unchanged. So 1 minus 1, 2, 4. Here I'm doing R, row 2. Row 2 is transformed row 2 minus 3, row 1. So therefore I should get 5 minus 7 minus 9. Here I'm doing row 3 and I subtract 2 times row 1. So I will get 0, 5, minus 7. Oh, sorry, here it was, no, this is correct. 5 minus 5, and here minus 5. Okay, let's take an example with this row. We subtract 3 times row 1. Okay, so starting from here, right? So this minus 3 times this, so we get 0. This minus 3 times this. Here we have a minus sign, so it's 2 minus 3, so it's plus 3, so it's 2 plus 3, it's 5. Okay, and minus 1. And here we do minus 3 times 2, so minus 6, so we get this minus 7. Okay, so this seems to work fine. The last one, yes. So 3 minus 12, 3 minus 12 minus 9. Okay, so that's how you get the row 2. Now, similarly, you get row 3. And once you have done this, where are you? Well, you just finished step 3. Okay. Now we move the cursor down and to the right. So I'm going to erase this part. Okay, so moving the cursor down to the right put us in this position. So this is our cursor. As you can see, this cursor is not a 1, okay? So we need to do something here to get a 1. Now we have 2 solutions. We could divide this row by 5, but we would get some pretty ugly fractions here. Or, as you can see here, we could divide by 5 and we will get only integers. So this is the solution we are going to choose here. So this amount, in fact, to swap. So we are going to swap row 2 and row 3. Okay, doing that, row 1b is unchanged. So 1 minus 1, 2, and 4. And therefore, second row is 0, 5, minus 5, and here minus 5. And here we get 0, minus 5, sorry, it was a 5, and then minus 7, and then minus 9. Okay. Now, what is a good point of this is that now I can divide row 2 by 5, which is one of the elementary row operation. What do I get? I will, so I don't modify the other row 1 and row 3, therefore I can write row 3 also unchanged, 5 minus 7 and here minus 9, okay? And this one just becomes 1, minus 1 and minus 1. Okay. Now, once I've done this, well, my second pivot is ready, as you can see. So, I'm going to make all the other entries in the same column equal to 0. Again, I will use the pivot to transform this entry and this entry into 0. How do I do that? So I will do two operations, obviously. First, I will transform row 1, okay? And what do? I do row 1, and I'm going to do plus row 2. This will be enough to cancel out this entry. And the row 3 will be transformed to get row 3 minus 5 row 1. Therefore, I will get 5 minus 5 equals 0. Okay, if I do that, what do I get? So, I should get the following. So, row 1 should become 1, 0, 1, and then 3. Row 2 is unchanged. Therefore, I get 0, 1, minus 1, minus 1. And row 3 becomes 0, 0, 1, minus 2. Minus 2, and here, minus 4. Okay, so as you can see, this is a pivot, this is the next pivot, and now I need to take care, so I finished actually, in my second pivot there is no other entries that are non-zero, and so I'm here. Then I move the cursor down one row and to the right again, so basically I move the cursor like this. Okay, so here, yeah, I don't have much choice. I'm going to divide this by minus 2. This row I divide by minus 2 to get a 1. Okay, so that's right here. So here, row 3 is transformed into 1 over, or minus 1 over 2 times row 3. Right. Okay, so what do I get? I get 1, 0, 1, 3. And then 0, 1, minus 1, minus 1. And then 0, 0, 1, and then minus 4 divided by minus 2 will get 2. Okay. Okay, that looks pretty good. I'm checking if yeah, this is correct. Now, so where am I? I got pivot 1, pivot 2, and now this is pivot 3. This is my new pivot. Now you know we are going to make the other entries in the same column equal to 0, and we will use the pivot for that. Okay, so the next operation, what is it? I'm going to transform row 1 and row 2. As you can see, row 1 will be changed to row 1 plus, so I'm using this pivot, right? So I'm going to do minus row 3. And here, row 2, I'm going to just add plus row 3 to get a 0. Doing that, I will get the following. So row 1 is becoming 1, 0, 0, and then 1. Then row 2 is becoming 0, 1, 0, 1. And then row 3 is 0, 0, 1, and 2, unchanged. Okay. Here I have made all the other entries in for my third pivot equal to 0. I move the cursor down one row and to the right, but look, I cannot go down anymore. So I'm finished. This is our REF. Okay. Now we need, remember, we started from a system of linear equations and we are looking for the solutions of this system. So how do we read, in fact, the solutions using this REF form? Okay, this is very simple. Remember that each column is attached to a variable. So the first column is attached to the variable x. This one corresponds to y, and this corresponds to z. First thing. Second thing, remember that we have two kinds of variables. We have the pivot variables and the free variables. Pivot variables correspond to columns where there is a pivot. So let's write down our pivot. This is a pivot, this is a pivot, this is a pivot. Here you can see that x, y, and z are pivot variables. Which means that I have, in fact, in this case, no free variables. Okay, so I'm going to use this augmented matrix and transform it into a system. How do I do that? Well, for example, the first row of this augmented matrix is 1 times x plus 0 times y plus 0 times z equal 1. So I'm just going to put 1x equal 1. Second, 0 times x plus 1 times y plus 0 times z equal 1. Therefore, I get the equation y equal 1. The last one, 0 times x plus 0 times y plus 1 times z equal 2. I get the equation z equal 2. Okay, as you can see, this gives me immediately the solution. There is a unique, so the final answer is that the solutions of my system S, this is a unique solution. So remember, if I write the equation in terms of in terms of matrix, AX equal B, my X will be the vector column with coordinate 1, 1, 2. 1, 1, 2. And there is a unique solution. So it's a set of solutions, okay? So I start with this bracket, this is a set, and there is only one solution, which is this column vector 1, 1, 2. You can also we can also write solution of S equal 1, 1, 2. This is also fine. Okay, you can write as a column vector or as a row vector. I don't mind. As we have seen in the previous session, it's not always the case that the set of solutions will be a unique solution. So to illustrate this, I would like to take example 2. Okay. So I'm going to erase this. We will still apply this algorithm, but I need some space. So this will be my example 2. So let's take another example. So I'm going to start from the augmented matrix. Alright, so here we start from the following matrix: 1, 2, minus 1, 4, 2, 1, 1, 6, 5, 4, 1, 17. Okay, so here, as you can see, we have already the first pivot. And therefore we go to step 2, which is to transform this and this into 0. How do we do that? We will do the two following operations. So first of all, row 2 will be transformed into row 2 minus 2 row 1, and row 3 will be transformed into row 3 minus 5 row 1. Okay, if we do that, we will get the following: 1, 2, minus 1. Okay, so sorry, it's an augmented matrix, so I should put a vertical bar here. 1, 2, minus 1, 4. And then 0, minus 3, 3, minus 2. And then 0, minus 6, 6, minus 3. Okay, now what do? I move the cursor down and to the right. Okay, so I'm here. And I'm going to transform this into a pivot. Well, again, I could divide, if I divide by 6, as you can see here, I will have anyway a fraction here. Okay, so here I'm just going to divide by 3, the second row. Okay, so we modify row 2, and we will do minus 1/3 of row 2. Doing that, we get the following. Okay, so I just modify row 2. 1, 2, minus 1, and 4. And then here 0, I get my 1 as I wanted, and then here I get minus 1, and then here I get 2/3. Then row 3 is unchanged, so 0, 6, minus 6, 6, and minus 3. This is my new pivot. And again, we are going to eliminate this entry and these entries. Okay, so here I will modify row 3. Modify also row 1. Row 1 will be row 1 minus 2, row 2, and row 3 will be row 3. So row 1 minus 2, row 2, and row 3 will be row 3 plus 6, row 2. So doing that, I will get the following matrix: 1, 0, 1, 8 divided by 3, 0, 1, minus 1, 2 divided by 3. Yes, that's correct. And then finally we will get, let me see, 2, 0, 0, 0, and 1. So transforming this row 3 by row 3 plus 6 row 2, we get this very nice last row, 0, 0, 0, 1. Okay, now we move the cursor to the right. As you can see here, this is not a pivot. And remember, the RREF form is not always a regular stair. The steps of the stairs can be longer. So if you cannot catch a 0, there is no way you can transform this 0 into something else here. So you have to go here. This is your next pivot. So this is actually almost REF form. This is our the pivot of our last row, and therefore the last two operations is to replace these by zeros. As you can see, because here we have only 0, then these entries will not be modified, and this will be modified to 0. So you can immediately predict, in fact, what will be the REF. The REF will be 1, 0, 1, 0, 0, 1, minus 1, 0, and then 0, 0, 0, 1. Okay. This is, with practice, you can immediately deduce this. If you want to go slowly, this is also fine. Then I modify row 1. And how do I modify row 1? I'm going to remove 8/3 of row 3. And I modify row 2. Row 2 is row 2 minus 2/3 of row 3. The result will be exactly this one. And the reason is that here, here, and here you have zeros, so these three first entries are not modified in fact, and these are replaced by 0. That's why you get this form. So this is REF. Again, we want to, so we have transformed, remember, we started from one augmented matrix, and, sorry, I forgot a vertical bar here, okay? Yeah. And then I want to read the solutions. I know that because I have applied some row elementary operations, the set of solution is not modified. Therefore, the set of solution of this augmented matrix is, remember, the same as the original augmented matrix. Now here, how do I read that? Well, same way. I'm going to give a name to the variables. So this variable will be called x, y, and this one z. Now, as you can see, here, what do I get? I get something quite strange. I get 0, 0, 0, and 1. What does it mean? It means, in fact, this equation means 0 times x plus 0 times y plus 0 times z equals 1. But you see, this can be read as 0 equals 1. Impossible, okay? This is impossible, obviously. What does it mean? It means actually that the system is inconsistent. Okay, one solution, and second example, we find actually 0 solution, okay? Good. Now, I would like to finish this session with some application of the method to solving another problem. All right, so let's call this section application of the Gaussian elimination that's right. Okay, so here we start with the following theorem. Let S be a system of equations in n variables. So same number of equations and variables. Assume that this system corresponds to the matrix equation AX equal B. Where Aij is a n times n matrix. Then, if A is invertible, then the system admits a unique solution, given by x equal a minus 1 times b. Yeah, this is actually obvious. Okay, this theorem is absolutely obvious. So let's go to the Gauss-Jordan theorem. Okay. Again, we start by S, a system of linear equations corresponding to the matrix equation. So we are going to use the letter AX equal B. So here A will be a matrix with entries Aij, and X is X1, Xn, and B equal column vector B1, Bn. Now, the augmented matrix so here I'm going to form the following augmented matrix. It's a little different from the previous one. We put on the left side A, and on the right side we put the identity matrix, so not only a column of B's. In fact, we forget the B's, and we just put another matrix, which is the identity matrix. This this augmented matrix is row equivalent to identity and matrix C if and only if if and only if A is invertible with inverse. So the inverse of the matrix is usually denoted A to the minus 1. This will be, in fact, equal to C. So this is the Gauss-Jordan method, in fact, to calculate the inverse of a matrix. Once you have calculated the inverse of the matrix, you will be able to solve your system very easily. Okay, so this gives you a method, okay, to solve a system of n equations with n variables, only in this case. And the method is as follows. By the first theorem, I know that the solution will be given by this computation, so I just multiply the inverse of A by the column matrix B. And how do I calculate the inverse matrix? Well, I will use my Gaussian elimination algorithm to transform this augmented matrix into this one. Why? Because the final result here will be precisely the inverse of A. Okay, so this combination of the two gives a solution of how to solve a system of n equations in n variables. Let me give an example of this method. Okay, so you will do the following exercise concerning this method. Start from this setting. This is A, and here we have the identity matrix. And apply your row elementary operations to get at the end here the identity matrix and here the matrix that will be in fact the inverse. So I'll let you find the solution for this one. And I would like to finish with a third example. So as you can see, in this session we have seen so far one example where we had a unique solution, one example where we had the system was inconsistent, so zero solution. I would like to show you a last example where we will have, in fact, infinitely many solutions. So this is last example. So here the system consists of the following equation: x plus 2y equal 1, z equal 2, and 0 equal 0. Okay, so first we transform this into an augmented matrix, right? Okay, so the augmented matrix in this case is the following. Okay, we have how many variables? We have 3 variables. So we will have 3 variables plus 1 variable, 1 column of b's. First row will be 1, 1x, 2y, and we don't have z, so we have 0 here. Then equal 1. So this gives the first row. The second row is 0x, 0y, and 1z. So 1, and here we have 2. Finally, the last row is 0, 0, 0, 0. Okay, now let's have a look. Is this RREF? Here we have our first pivot, 1, and as you can see, in the column, the only non-zero entry is the pivot. So this is fine. Next one, well, the next pivot is actually here. Not here, but here. And the other entries in the columns are 0. So this is fine. Then the last one, no pivot, but all entries are 0. The a row consisting only of 0 entries should be at the bottom. So this is okay, and this is perfectly RAF. So this is RAF, which means that we are ready to read the solutions of the system S. How do we do that? So we write again the equations with the following form. We will write pivot on the left side of the equation in terms of 3. So, what do I mean by this? I mean the following. First, let's determine which variables are free and which variables are pivotal. So, as you know, the pivot variables correspond to the columns where I have a pivot. So, column 1 and column 3. Let's give a name to this variable, x, y, z. As you can see here, x and z are pivot variable. And therefore, everything that is non-pivot is a free variable. So y is a free variable. Okay? So I'm going to write on the left side of the equation, of each equation, here I have 3 equations, in fact, the last one is unnecessary equation, we don't need it. So let's start by 1. Free, so I write pivot in terms of free. So I'm going to write 1 times x, so x. So this will be, of course, the same equation as here. So here, x plus 2y equal 1, but I want to write pivot in terms of free. So I'm going to move the free variable on the right. So I'm going to, instead of writing x plus 2y equal 1, I'm going to write x equal 1 minus 2y. Okay, that's the same equation, but it will be easier to read at the end the solution. Here, well, I cannot do anything else. It will be z equal 2, isn't it? And here, 0 equals 0, I can forget. This is true, and I can forget about it. Okay. Now, this is enough to calculate the set of all solutions. How do I do that? So the solutions of my system S, in this case, will be the set, so it's a set of column vector or row vector, but which vector? So first of all, these vectors will have 3 coordinates, x, y, and z. Okay, so let's write it as a row vector. The first one will be 1 minus 2y. 1 minus 2y. So I write the coordinates of the solution vectors in terms of the free variable. This is the key. Now, y is free. What does it mean? Free means that it can be anything. So I write the free variable as it is. Sometimes you will have several free variables, but so you will write them as they are. And the last one, well, z equal 2, so this will be this. So the set of solution of this system is actually the set of triples of the form y minus 2y, y2. And you have to say, what is y? Well, y can be any real number. This is the set of solutions of my system. As you can see, there are infinitely many, because each time I plug in a value for y, I will get another solution. So you can put y equals 0, you will get one solution. You can put y equals 1, you will get another solution, and as many as y varies along the real numbers. Okay, so we have seen example where we had one solution, unique. Example where we had 0 solution, so-called inconsistent system, and here you have an example where you have infinitely many. So remember, when same, you do the RREF form, and then you rewrite the equations in the form pivot on the left equal 3 on the right, and then you write your set of solutions following these equations. Thank you.